So far we have seen how to find the Laplace of any given function as long as the function is piecewise continuous. And later we saw that, right? We may have some other easy rules we can use when I have the sum of the functions when you want to take the Laplace of transformation. But where do I know, right, if I can guarantee, right, when I want to take the Laplace of the functions, who can guarantee, right, I can find the result of this integral? Does this exist? And yes, we didn't have any problem, right, for the elementary functions, but there is no guarantee right around if I have always this integral. When I have the piecewise continuous function, I can only guarantee I'm going to have the right this integral, but if I don't have any right bounds on f of t, this integral still can escape to the infinity, right? That is why, guys, I need to bound these functions, right, so that there will be no problem, right, about that type of big numbers. So I can guarantee that I have the integral. That is why we are going to define a new concept we call the exponential order alpha. Exponential order alpha, just to eliminate this type of problem so that I can bound, I can put a restriction on an f of t so I can guarantee, okay, I have this integral and there is no problem about the convergence of this integral. What it says, look at that. Let's say I have a function and I'm going to call this function exponential order alpha if there exists such a positive numbers f of t should be less than m times e to the alpha t for all numbers bigger than big T, guys. As you see right in this inequality, I'm trying to restrict my f of t by an exponential function, and then I have here the alpha number. That's why, okay, we're going to call the function exponential order alpha. Let me give you an example. Let's say I have f of t, which is equal e to the t cosine 3t. Can I bound this function in this way? Okay. Since it is e to the 2t cosine 3t, I know cosine 3t, right, is always less than 1. If I use, right, this inequality, my f of t is going to be less than e to the 2t, correct? Here, m is going to be 1, but the t could be any number bigger than 0. As you see, I can call, right, the f in this example exponential order 2, correct? But my main problem here is to show, right, if the Laplace transformation exists. To do that, of course, I'm going to use this definition, the new definition, exponential order alpha, but I need to prove, right, as long as I satisfy this definition and also the piecewise continuity of my function, you're going to see, which we are going to use this new theorem, guys, you're going to see this integral will exist. So let's say I have f of t. As I said, it is a piecewise continuous on the interval I'm going to be working on. And also, this function is exponential order alpha. Then, look at it. If you satisfy these two conditions, then I can claim and I can guarantee that the function transformation exists for these numbers. Okay, we're going to prove this theorem. What we claim this. The Laplace of, right, the function, which needs to be given, right, by this definition, should exist. Exist meaning actually it should be convergent, right? It should be convergent. So I'm asking if it is convergent. How am I going to show if it is convergent? So from the integral features, if you remember, I have such a rule. I can break it down, right, in this interval. So I can use any number. In this case, I'm going to choose the t, big T. And the second integral, right, will be in this interval. So in this interval, guys, in this interval, since the f of t is piecewise continuous function, I don't have any problem, okay, taking the integral of this one. So that part is convergent. So this part also, I can say this integral exists. I don't have any problem on the finite interval. But when it comes to the second part, I need to guarantee, okay, I don't have any problem for the second part, guys. So I don't have any problem for the first part, but for the second part, I'm going to be using, look at that, the improper integral definition, again, t to the n, e to the negative st f of t dt, correct? At this step, I'm going to use the exponential order alpha feature. So if I use it, look at that, since this function, right, is less than m times e to the alpha t, I can use another integral feature, right, to write in this way. So m times e to the alpha t dt, right? I use the exponential order alpha feature of f of t. And look at that. Can I take this integral? Yes. This integral will be equal e to the negative s minus alpha t over s minus alpha. You will remember, right, that we solved the Laplace transformation of e to at, which we applied, right, the same integral. You can just look at that part. Also, you can remind yourself, okay, how to take care of the right exponential functions integral. This is the integral of this type of function. Since here, look at that, I can combine the s and then alpha, and then since, right, I am taking the integral with respect to t. Okay, now, if I use my bounds, correct, this bound and then this bound here, and then for the first bound, which is n, right, I'm taking the limit, that part will go 0. And then for the t, look at that, I'm gonna have this integral, this result, limit n goes infinite, m times e to the negative s minus alpha t over s minus alpha, and then that's gonna be equal, since look at that now, there's no n here, that's why, okay, this integral will be equal t over s minus alpha. So this number is, right, the finite number, so I can just say, right, this is convergent integral. So I may have missed, okay, a negative here. We should be careful. Here I have a negative. Did you see that? So now the second part of my integral, my Laplace transformation, gave me just a number which is less than infinite. That is why I can say that the Laplace of f of t, right, I can guarantee that this integral, right, now exists as long as f of t is piecewise continuous function, and also f of t is exponential order alpha. So I can say that Laplace exists.